Trace-based programming. In this video, we will see how to systematically construct a program from its traces. The prerequisite for the application of this method is that you as programmer already have a mental representation of the algorithm that you want to implement. This means you can execute it by hand. The method roughly proceeds as follows. First, you execute the algorithm for an input. Next, this execution is converted into a trace table. In the third step, the rows of the trace table are generalized to obtain the operations of the program. In step 4, the control flow is mechanically derived from the trace tables. And in the final step, decision trees which govern the control flow must be found. The advantage of writing programs in this manner is that different aspects of the program are constructed separately instead of having to think of them at once. In general, it turns programming into a more structured process. As an example, to demonstrate the method, we shall look at division on binary numbers. On the right, you can see an example to refresh your memory of what you probably saw in elementary school. To express this algorithm, we can use the following basic functions. The constants 0, 1, equality and addition, the empty string epsilon, strings for 0 and 1, and equality on strings, and also concatenation indicated by a circle. Then the length of a string and get, which returns the character at index I. And last but not least, we can compare and subtract binary numbers. Now we can begin with the first step of the method, which is to execute the algorithm by hand. We do this for the shown input. This is the result, and these are the decimal representations of the binary numbers. As a reminder, the number 2409 is called dividend, the number 13 is the divisor, and 185 is the quotient, and 4 is the remainder. First, we copy the first digit of the dividend. Since the divisor does not fit into the number on the bottom, we copy the next digit. And again, and again, and one more time. Now the number on the bottom is larger than the divisor, so we append a 1 to the quotient and subtract it. We continue with the result of the subtraction plus an additional digit from the dividend. Again, since the divisor does not fit, we copy the next digit of the dividend. This time we also append a 0 to the quotient. We didn't append a 0 before because leading zeros can be omitted. Since the divisor fits, we append a 1 to the quotient and subtract the divisor again, and continue with the result plus an additional digit. Again, the number on the bottom is larger than the divisor, so we append a 1 and subtract. And this continues. This is the final time the divisor fits into the bottom number. We append 1 to the quotient, and the result of the subtraction is the remainder. Now the execution of the algorithm has finished. We use the following variables for this algorithm. We call the dividend A, the divisor B, the quotient C, and the remainder R. Additionally, we use a variable I, which keeps track of how many digits from A we have read, and the number on the bottom is called X. The next step is to write down the previous execution as a table. Each row contains the values of the variables after one execution step. The first row contains the input. Then the algorithm initializes I with 0 and the remainder x and quotient c with the empty string. Since the values of a and b do not change, we hide these columns to save some space. Now we copy the first digit of a. This means x equals 1 and I is also 1 because one digit of a has been read. If we leave a cell blank, this means the value has not changed since before, and we copy the next digits. Since x is not smaller than the divisor, we append 1 to c. Then we subtract b from x, bring it up and get the next digit from a. Since x is smaller than b, we append a 0 to c and copy the next digit. Now x is larger than b, so we append a 1 to c. Then we subtract again and get the next digit from a. We append another 1 to c. And subtract again, bring it up and get the next digit. Again we append a 1 to c. Since there isn't enough space to show the whole table, we hide the first couple of rows. And the algorithm continues as before. And in the final step, r is set to 100. Our next goal is to find the program operations. We do this by generalizing the rows in the trace table. In the first row, after the input, we simply initialize the variables. Let us call this operation init. In the next row, we increment I and copy a digit from a. Notice that the I in the expressions refers to the value it had in the previous row, which was 0. We call this operation get. The next operations are gets as well. In this row, we append 1 to c. We call it res1. To get the values in this row, we subtract b from x and copy the next digit from a. We call this operation get2. Next, we append 0 to c. We call this operation res0. Then again a get, and these two operations are res1. And these two operations are get2. Now we can continue with the rest of the table. If c is changed and ends with 1, it must be a res1 operation. And if it ends with 0, it must be res0. After res0 comes get, and after res1 comes get2. And in the final row, we set the remainder to x minus b. And we call this operation rem. We found the following operations in the trace table. But are this really all operations? We can try other inputs and see if the operations that we found suffice to describe them. For example, 1 divided by 1. We start with init, then get to get the next digit, write a 1 to see, and finally set the remainder at the end. So in this case the operations suffice. How about 0 divided by 1? Again we initialize, get a digit, append a 0 to C, and then we must set the remainder. The only operation which affects R is rem. But this gives us the wrong result, 0 minus 1. And we expect the result to be 0. The same problem occurs for this input. To solve it, we add another operation which sets R to X. And we call it rem0. And we rename rem to rem1 for consistency. So now, if we are confident that we have found all operations, we can continue with the next step. Using the information contained in the traces, it is possible to construct the control flow of the program. Depending on whether the traces exhibit all of the flow, this might only yield a subgraph of the complete control flow. Let's look at the first trace table again. We only need the column with the operations. And here's the rest of the column. Next, we need to draw a vertex for each operation. Since init is the first operation, we draw an arrow pointing to it to indicate that it is the start operation. Then we look at every pair of operations that occur consecutively and draw an edge between them. The first such pair is init to get. Then get to get. And the next pairs are the same, so we can skip to the next new pair, which is get to res1. And then we continue with this procedure. Then we also have to look at the second trace where we had the operation rem0. From there we get the edge from res0 to rem0. This control flow graph is an intermediate piece of information that helps us to build the decision trees in the next step. Now we can construct the last part of the program, which we call binary decision trees, or BDT for short. Each operation must have such a BDT which determines with what operation the program continues or whether it should halt. But before one constructs these trees, one should ensure that no edge is missing. So the BDT for init consists of a single node, which is get, since after init, get must always follow. Similarly, after rem0 and rem1, the execution halts, so their BDTs are just a single node tree halt. A more interesting case is the BDT for the operation get. It can either go to itself, to res0 or res1. Recall that in the algorithm, after we copied a digit from the dividend a, we checked whether x is larger or equal to a to decide what to do next. So this condition, which we also call predicate, will be the root node of the BDT. If x is larger than or equal to b, then we know we have to append a 1 to the result. Hence we need to go to res1. If x is smaller than b, we either continue with res0 or get. Recall that we said we do not write leading zeros to c. So if c is not empty, then we have to append a 0, so we go to res0. However, if c is empty, This does not necessarily imply that we skip writing a 0 and go to get again. Think of the following two examples. If the result of the division is 0, then we have to write a 0 even though nothing has been written to C before, and so C is empty. So to see if this condition is met, we check if all digits of A have been read. This means we check whether I equals the length of A. If this is the case, then we go to res0 and otherwise to get. Suppose you made a mistake and instead of checking for I equals the length of A, you simply wrote get instead. After you finish constructing your program, you should execute it to see if the traces produced by the program match the ones that you wrote manually. In this case, you would see that for the input 0 divided by 1, the program's trace does not match the manual one, meaning that the program contains an error. Moreover, it would directly point you to the node of this binary decision tree, so that you could fix it. Next, we look at get2. It can go to either res0 or res1. To see whether to append a 0 or 1, we check if x is larger than or equal b. Now we look at res0. Only get or rem0 can follow. And we go to rem0 if we read all digits from A and otherwise to get. For res1, the BDT is similar. So now the program which implements binary division is complete. The binary decision trees, together with the operations, are a formal and complete description of the algorithm. Let me make some final remarks about this method. As mentioned previously, the operations and BDTs describe an executable program. While the control flow graph is not required in the sense that it can be derived from the BDTs, its utility lies in the fact that it can be used to visualize the flow of the algorithm. The application of this method only makes sense in the context of algorithms with a non-trivial control flow. For example, a function that can be described by a non-recursive expression or using only a single operation does not gain anything from this method. Two problems that one should look out for and that cannot be detected by comparing the program's traces against the manually written ones are missing operations or missing transitions in the control flow. To prevent missing transitions, one can go through all pairs of non-adjacent vertices in the CFG and try to come up with a reason why such a transition does not exist. Something that was briefly mentioned is that by verifying the program's traces, the BDTs are also checked to see if they point to the correct next operation. The price of writing traces by hand only pays off if the program is verified against them. In fact, the method in general can be seen as an extreme form of test-driven development where the traces are the test cases. As a rule of thumb, one should strive to use the minimal number of operations when implementing an algorithm. This is in line with the simple mantra, the shorter the code, the less likely it contains bugs. Together with our previous remark about when to apply this method, it also implies that it should only be used when deemed necessary rather than indiscriminately. The purpose of this method is not only to prevent one from making mistakes during development, but also as means to demonstrate that the program indeed correctly implements the desired algorithm to somebody else. In this regard, I hope I was able to convince you that the previous program does indeed correctly describe the division algorithm. So, this concludes the presentation of the trace-based programming method, and thank you for watching.